All right. Lecture 6. Let's get started. All right. There we go. That's better. Okay. A couple of housekeeping items. So I believe homework 2.1 is still being graded, but the solution should be live now. How did 2.2 go? Hopefully it was repetitive, like it sort of felt like the same thing over and over again. I think that there were a total of 11 paths, something like that, but there's also symmetry. Like if you have a path like that, the same path is mirrored. So yeah, but hopefully it was pretty straightforward and it was pretty easy to decide which one governed. Just so everybody is aware, we're sort of approaching what I would call, quote-unquote, real problems, and by that I mean we've been taking tension members and sort of attacking each little piece of them, and then starting Wednesday, we're going to start doing the problem start to finish. So we have one more day of sort of, I guess I would call it either background material or modular style material on tension members, which is to look at shear lag factors and slenderness. That's going to be our goal today. And then with that, we'll have enough background info so that we can start going at tension members start to finish on Wednesday. The only other two things I would mention is ASCE, they're having their first meeting on tomorrow at 5 p.m. in that room right over there. So they have free food, which is always awesome. And then also I would mention that today at 2 p.m. we have a faculty candidate for our open position in environmental engineering, and they will be doing their presentation today at 2. So if you have time, come. All right. Any questions? Everybody get the code? Okay. All right. Lecture 6. Okay. So let me sort of take a step back because I want to make sure that you see the big picture of what it is that we're doing. So this entire idea of steel design, particularly if we're talking about strength design, is all focused on evaluating limit states. That's really the be-all, end-all goal of structural design. In other words, to determine that our factored resistances are greater than or equal than our factored loads. Now, factored loads come from two, well, I guess you could say 3 areas. So the first is we have to actually determine, where those loads come from, and so that's, like ascertaining wind pressures and live loads and things like that. We then do structural analysis to get the load on a given component, and then we then factor those loads to get a factored load. The resistance is what we are sort of indirectly, or what we've indirectly been spending the last few lectures on, determining how strong the member is. In terms of the factored resistance, what we do is we will end up evaluating several limit states and taking whichever capacity governs. And so for right now, we've been focusing on 2 limit states related to capacity in the gross section and the net section. And then what we did from there is we said, well, we can define a capacity of gross section yielding, we can define a capacity of net section fracture, and we ultimately get equations like this. And what we've spent the past couple of lectures on is the net area and the gross area, right? Fy and Fu, those are lookups. We can just look those up in the specs. Those are pretty straightforward. So the one thing we have yet to talk about in really significant detail is this term U, right? And so once we figure out what's going on there, we can start doing problems start to finish, okay? And so that's our goal, one of our goals for today, I should say, is to discuss U and to discuss what these shear lag factors are. I talked about this a little bit last time, and I would say that I'll give you a brief little highlight from last time. So I'm going to shut this in case I'm belting out steel design out the hall. Okay, so we talked about this last time, the idea that if you were to actually investigate the stresses around a connection, what you'd find is away from the connection, the stresses are pretty uniform, right? But when you get to the connection, right there at the connection, the stresses are kind of wonky. Like they're discontinuous, they're non-uniform, and unfortunately, if we're looking at fracture in the net section, we can't ignore that, okay? What we're doing is we're samurai sorting or lightsaber here or here, right there along the net section. And we can't really ignore the fact that the stresses are non-uniform. But it's also very computationally expensive. It takes a lot of time, a lot of effort to accurately model these, and so we need a way of handling it. We need a way of handling it fast. And so the way that we handle that is this. What we do is we take the net area and we adjust the net area with what's called a shear lag factor. Okay? So these are shear lag factors, and basically what we do is we say, for a given amount of net area, how much of that area is effective in transferring stress? And that's what shear lag factors are for. Now, excuse me, forgive me, I'm dealing with a sinus infection right now. Okay, so if you have your manual with you, I would turn it to this page now. This is page 16.1. -34, so this is in Chapter D. This is in the back part of the manual. This is a page that I would tab. Okay, I would definitely put a little sticky note in your manual for this page because we are going to use this quite a bit in tension member land. Okay, excuse me. I should mention right off the bat that these equations are largely empirical. Okay. In other words, while there is some physical, I guess I should say, physical reasoning behind why the formulas are the way they are. In other words, like for example, if you look at case 2, you'll see that the connection length is in the denominator, and there is a good reason why it would be in the denominator as opposed to the numerator. While that stuff is still true, these are empirical. And by empirical, you know, go down to the lab, test a bunch of specimens, and curve fit an equation that fits the data as best as possible. That's not the same thing as a mechanistic style expression where we can break out a chalkboard and some differential equations and derive an expression. Empirical expressions aren't really derived as much as they are curve fit. And so these are largely curve fit empirical expressions. Okay? Now, the way the table is organized is there are several cases here on the left. So you'll see like case 1, case 2, case 3, case 4. For each of these cases, there's a description of what the case means, and then there's an expression for the shear lag factor. I should mention that it is possible that multiple cases will apply to a given connection. Okay, the biggest reason why you'll get multiple cases is because case 1 and 2 are really the ones you should pay attention to first, and then cases 3 through 8 are sort of special circumstances of case 2, and that seems like a lot, but let's sort of digest what's going on in case 1 and case 2. Okay, so if you read case 1, okay, so here's the table, and what I've got here is I've got here case 1 and case 2, and I sort of paraphrased it a little bit, but if you read the language in case 1 and case 2, there is actually a very explicit difference. Okay, so case 1 says if the load is transmitted to all of the cross-sectional elements, then we take U to be 1. Okay, so an example of what I would mean by case 1 would be, let's say I have, I don't know, like an I-shaped cross-section, okay? And let's say I have bolts through this, through this, through this, through this, and through that, through all of the cross-sectional elements, okay? If that's the case, we would go ahead and take U to be 1, okay? In other words, are the stresses discontinuous? Yes, there is some non-uniformity, but not enough for there to be an appreciable reduction in efficiency or a reduction in effectiveness of the cross-section, okay? So this would definitely be a case 1. Whereas a case 2 may be something like this. In other words, the flanges are connected but not the web. This is a very common, somebody taking the picture and pose for it. Get it? Good. Okay. This case, the one I have here on the right, that is a very common way of connecting wide flanges for bracing elements in building systems. And this would be an example of a case 2 type connection. Okay? So the difference between case 1 and case 2 is case 1 says all of the elements, cross-sectional elements, are connected. Case 2 says some of the cross-sectional elements are connected. Now, of course, there's an all, there's a some, there's not a none, because you have to have something connected to something in order for there to be a connection. So case 1 and case 2 are really the ones that you should sort of look at first for any given connection, then go to the remaining cases and see if they apply. Now, one of the things that I do have maybe a slight bone to pick with the manual is sometimes I think they could be a little better in terms of the fonts that they choose and the symbols that they choose. Because if you look at the equation for case 2, it says 1 minus x bar over slash. You know, you can't really tell what that is. Okay, what that is an L. Okay, and the way that I've written it is I've said that it is 1 minus x bar for the connection and L for the connection. Okay, so I'm doing that so that you know what those terms mean. So I am using a slightly different notation than what's in the manual, but I'm doing that so that we understand what those terms are. Okay, so if there is one bone or one gripe I have with the manual, I wish the symbols that they used or the fonts that they used had a little bit more clarity to them. But especially when you're first learning this science. When you're first learning it. I will tell you that case 2 is probably one of the most common cases that applies to tension members, so we really do need to take a look at what these terms mean because they have very specific meanings. Okay? In other words, like I have your X bar, okay, and your thinking is right now is probably, oh, if I have a member, I look up X bar for that member. Not necessarily. It might be Y bar. It might be a value that you have to compute. Okay, it's not X bar. I'm calling it X bar sub COM because you need to determine what that quantity is. Okay, so I have specific names for these. I'm calling these the connection eccentricity and the connection length. Let's start with the connection eccentricity, okay? So this X bar term is the distance from the connected face to the centroid, okay? That's how I'm defining X bar here. That's how the manual defines X bar, okay? So in other words, let's look at a few representative cases. For example, if I look here at the channel, the C shape here at the bottom. So I have a section that is definitely going to be case 2 applicable because only some of the cross-sectional elements are connected, in this case the web, but not the flanges, okay? And I propose that my connection eccentricity is from the connected face to the centroid. So the centroid for a channel is going to be somewhere about like right there. So for a channel, the centroid is not on the shape, it's out in space. And the connected face is this face right here. And I'm saying it's that face because this channel is going to be connected, like there's going to be a plate out here that it's connected to, right? So the connected face is that plane of the channel that's actually being connected to something, right? And so I'm saying that this distance right here, that distance is X bar sub CON, okay? Now for a channel that happens to be X bar, okay? That just happens to be X bar. For an angle, that might not be the case. So for example, for this angle right here, this angle, the long leg is connected, and if the long leg is connected, it's X bar, but if the short leg is connected, it's Y bar, okay? So you just got to be careful which value that you're using. Okay, now I do want to show you something, and I'm actually going to pull up the manual for this because I really want this to be very explicit. Okay, so I have here the manual. Let's see. I don't know why those links aren't showing up. There we go. That's close enough. Okay, so let's look at the angles. Okay, and you'll notice that I've got an angle page popped up, and it doesn't matter what angle page I'm looking at. I can look at any one of these. You know, they're all going to be organized the same way. Let's just look at this. Okay, this is a good one. Okay, so here I've got the x-axis properties, and there you can see y bar. Okay, and over here on the next page you can see x bar. Let's use x bar. Okay, so let's say that I'm looking at an L 4x4 by 3/4. So I'm looking at this cross section. Okay, now if you look at the y-axis, okay, you're going to see a few terms. So this is the moment of inertia, this is the section modulus, this is the radius of gyration. Here we have this term right here, which we're terming the centroid, okay? But then there's also this term here, okay? I implore you, for tension members, do not use this x sub p. Do not use it, okay? I'm being a little fast and loose right now for what x sub p is. I will explain what it is later, okay? For now, just accept what I'm about to say, that this term is related to bending, okay? We're not bending tension members. We're yanking on, okay? I will get to what this means later, but for now, ignore this. Same thing for the for this term right here. Here's y bar and yp. Ignore the yp. Okay? Is everybody okay with that? Just ignore the yp. You'll understand what that means around March or April. Okay. All right. Everybody good on this? Okay. I do have a very special case for X bar. We're not going to deal with this today, but we will deal with this on Wednesday. Whenever you have a W section connected via the flanges, okay, which is, again, one of the most common connection scenarios in W section bracing, is that whenever we need X bar, what we do is this: we take the W section and we convert it into an equivalent WT, okay? And what we do is we convert it into equivalent WT, and then we look up the Y bar for that equivalent WT, okay? The reason that we do that mechanically is the idea is that if I'm yanking on the tension member like this, the idea is that half the load gets transferred up here and half the load gets transferred down here. And then what we do is we say, okay, we're looking at, let's say, this cross-section now. So this is the cross-section that we're looking at. And we're saying, what is the distance from the connected face to the centroid? And that's how we're getting that. Okay? Now, for a WT, that distance is Y bar. Okay? And by the way, what do I mean by an equivalent WT? Well, if I had a W12 by 30, the equivalent WT would be a WT 6 by 15. And how do I get that? Well, what's the difference between these two? It's half as deep, half as heavy. So I'm literally just taking the section, cutting it in half, and finding that out. And by the way, for every W section, there's an associated WT. That's where they come from. Okay? Does that make sense? So yeah, so if you're wondering where these come from, that's that. We're not going to deal with that today. We'll deal with that on Wednesday. Okay? Everybody good? Okay. As for the connection length is the out-to-out distance between center of bolt and center of bolt. Okay? And my main reason that I'm showing you this is that I do want you to understand that there is a difference between that dimension and this dimension, okay? And I'll tell you that this dimension is going to become important later when we look at block shear. But for now, I just want to go center of bolt, center of bolt. And I'm telling you this now because it's really easy to use the red dimension instead of this black one, but the black one's the one that we're going to use for shear lag, okay? Does that make sense? Everybody okay with that? Don't worry, we'll have some examples on this. Okay. Sound good? All right. Now, I do want to talk about slenderness limits because it's the one thing that we've yet to talk about before we could really start digging into tension member analysis and tension member design. So let's talk about it. Now, I put here tension or slenderness limitations or the lack thereof. And I want to explain what I mean by that by looking at the manual. So if you have your manual opened up to the shear lag factor table and you turn one page back to section D1, section D1 is the section on slenderness limitations, okay? And if you read the spec, what does the spec say right here? There is no slenderness limit, okay? And technically that's true, okay? However, I read the user's note here, and I want to talk a little bit about that. So let's read the user's note. User's note below says as follows. We're on 16.1-32. The user's note says, for members designed on the basis of tension, the slenderness ratio of the member as fabricated, taken as the fabricated length divided by the least radius of gyration, preferably should not exceed 300. Okay. These suggestions are in place for very specific reasons, and they have really nothing to do with strength, but they're more about really about the construction process. If members get too slender, they do kind of get a bit hard to handle, both in the fabrication space as well as on the construction side. If the member gets too slender, it can deflect under its own weight, it can excessively sag, it can lead to vibrations in the structure. And so even though the manual says there is no limit, we're going to adopt this limit in here, and most structural engineers do. One thing I'll tell you is that this is our first service limit state. This has nothing to do with safety or factored loads. This is more about day-to-day use of the structure. Okay? And what we're going to do is take the length of the member and divide it by its radius of gyration. Now, first off, let's talk about the radius of gyration. What is the radius of gyration? Well, first off, you can look that up for any member, but you could also compute it by taking the moment of inertia and dividing it by the cross-sectional area. Okay? So what is the radius of gyration? It's really just a normalized moment of inertia. If you know, remember, the moment of inertia is in inches to the fourth. So if you take inches to the fourth, divide it by an area, and then take the square root, you get an R value in inches. Okay? L over R is a great mathematical definition of slenderness because it's unitless, but it does sort of represent how slender an element is. So like, for example, if you had a soup can, the L over R is about 6. If you had a AAA battery, it's about 17. A normal piece of pasta is about 500, and who knows about Slender Man? That was a joke, not funny. But if you wanted sort of an understanding of what slenderness is, that's kind of what you're talking about. I mean, think of a dry piece of spaghetti that's really slender, okay? And how do you define that slenderness? Well, it's sort of a ratio between how long it is divided by, quote unquote, how big around it is. And how would you define that? Well, a great mathematical way of defining, quote unquote, how big around it is the radius of gyration, okay? So what we're going to do in this class is we're going to adhere to that user's note, and we're going to limit L over R to be less than or equal to 300, okay? Now, I'm going to tell you, right now, we're going to treat L over R as a slenderness limit for handling and for service and whatnot. What I can tell you is that for columns, L over R becomes much more important. And our limits on slenderness and how we deal with slenderness with columns and beams is much more different, much more stringent, okay? So, but we'll get to that later. For L is the member length, and I would just say pay attention to units, okay? Because if I have a brace and a frame, how long would you say that is? What units would you use to say how long that is? Feet, right? You might say it's 30 feet long, 40 feet long. Whereas the radius of gyration is going to be expressed in inches, okay? And L over R needs to be unitless. It is a dimensionless quantity. As for what do you use for R, okay? What I would say is if the section is symmetric, has some axis of symmetry, use either the minimum of Rx or Ry, and we'll have an example on this here in a second. If it's unsymmetric, and an example of an unsymmetric section is like an angle, use the minimum radius, and you'll see what I mean with angles because you can actually look that up, okay? So, I tell you what, I think we've done enough talking. Let's do some calculations. So, let me pull this up. So, these are going to be the two problems that we look at together. So, I have two sections, okay? I have a channel and an angle. The channel is a C10 by 30, and I'm going to determine what is its shear lag factor. I'm also going to determine if it meets suggested slenderness limits. If the member is 15 feet long, we're also going to look at computing U for this angle. So I threw in a parallel bolt arrangement and a staggered bolt arrangement. Okay? Does that sound good? Okay. So let's deal with the U value for the channel first. Okay? So that I don't have to keep scrolling and whatnot, I took the channel and I put it right here. Let's make it a little bit bigger. Here, I'll move this down. Okay, so here's our channel. Okay. So let's see. So let's all open our shear lag table up and let's see. Well, let me ask you a basic question. Do we think we're going to deal with case 1, or do we think we're going to deal with case 2? 2. Okay. By the way, do you see channels represented in any of the other cases, cases 3 through 8? And this isn't a trick question, by the way. Do you see channels showing up in any of the other cases? Which one?
4.
Is there a channel in case 4?
Just place angles, channels with welds at heels, T's, and W shapes.
Okay, but channels with what?
With welds at heels.
Okay, right. So while it's referenced, we don't have to use that because we're not connecting this with welds, we're connecting with bolts. So case 2 is the only case we're going to have to deal with, right? Okay? And case 2, our shear lag, so therefore, U in this case is just going to be U2. I can do better than that. So this is going to be our expression that we need to assess. Okay. So let's talk about X bar. The X bar connection. So let's go to a C10 by 30. And what we're trying to determine is the distance from the connected face to the centroid, right? So don't know why those aren't showing up. So what was it, a C10 by 30? Okay, so this is the left page. This is the right page. But actually, let's look at this diagram right here. Let's look at this. Let's look at that. Okay, so I'm trying to determine the distance from the connected face to the centroid. Now, by the way, the centroid, see how we've got this XX line and this YY line? Y'all see that? So that's the centroid right here. And so the connected face is going to be right here. So which term is the distance from the connected face to the centroid? Which term in the schematic are we going to be looking at? X bar. Okay. And so for a C10 by 30, which is this shape right here, we look up the X bar, and we get what? 0.649. Does everybody see that? So that's our value. Okay. For this connection, what is the connection length? Remind me, what did we define as the connection length? We say center of bolt hole to center of bolt hole. So what distance is that going to be for this connection?
6 inches.
Oh, I guess I should have clarified. Along the path of the load. So in the direction of the load.
9 inches.
9 inches. Okay. So we're talking about this distance right there. My big thing that I wanted to get across is that it's not 11. Okay. By the way, this 11-inch term is going to be important later when we look at block shear. Because block shear, we are going to need to know this total distance. But for now, it doesn't matter. So therefore, what do we get? And we'll say 3 decimal places for this. Making sure everybody's awake on this wonderful Monday morning. 0.928. Do I have a second? All right. Okay. Is that fair? Is that doable? That's not too difficult, is it? Okay. All right. Before we move on to the angle, let's look at this next question. Does the channel meet suggested slenderness limits if it is 15 feet long? Okay. Let's look at slenderness limits. Okay. Remind me, our suggested slenderness limits say that L over R needs to be less than or equal to what? 300. Okay. How long is the tension member in this problem?
180 inches.
Okay, yeah, because it's 15 feet or 180 inches. I'm glad you did that. Now, what about its minimum radius of gyration? Okay. Well, its minimum radius of gyration is really just going to be the minimum of Rx and Ry. So, let's make sure we can find these. What is Rx for our section? .43. Do I have a second on that?
Yeah.
Okay. What about Ry? 0.668. So, there we go. By the way, I should mention this moving forward. So, later on, I might not use the terms x-axis, y-axis. I might use the terms major axis, minor axis. I might use the terms strong axis, weak axis. All means the same thing. Okay? Which is the minor axis or the weak axis? The one with the least radius of gyration. Why does the least radius of gyration matter? Because which is going to give me my worst case slenderness? The one with the smallest denominator, right? Does that make sense? Okay. So therefore, and for this we'll do, I don't know, like 1 decimal place because I think the point will be made. What do we get for this?
269.5.
269.5. Is that okay? Okay, so I'm going to show you some notation that we're going to use a little bit later. So I'm going to say L over R is less than or equal to 300. Therefore, I'm going to use the term okay. And I'm either going to use the term okay or the term NG for no good. Okay? So it'll either be good or not. Okay? Does that make sense? So you'll see me use that here in a little bit. Okay. Does anybody have any questions on this? Yes.
How did we come up with case 2?
How did we come up with case 2? Okay. So the difference between case 1 and case 2. So when you look at the anatomy of that table, it's either going to be case 1 or case 2, and then the rest of the cases may or may not apply. As for the difference between case 1 and case 2, case 1 says all of the elements are connected. Case 2 says some of the elements are connected. And what I'm saying is there's no bolt through the flanges. So because there's no bolt here or here, some of the cross-sectional elements are connected, not all, and we're in case 2. That's a good question. So, any other questions? Good stuff. Sound good? Okay, all right. So now let's do our angle. Made that a little bigger. For the angle, we're just going to look at shear lag. We're not going to look at slenderness. I mean, we can if you want, but I didn't say how long the angle was. So there's a, like, one thing we could do is we could figure out what is the maximum possible length of the angle that meets slenderness limitations, but we'll talk about that here in a bit. So, going to the question that was just asked, is this going to be a case 1 or a case 2? Case 2, because this leg's connected but not this one. Are there any other cases, though, for this one that apply? Like, is there anything in 3 through 8 that looks like it's going to apply? Say it again?
Number 8.
Case 8. Ooh. So, what does case 8 say? Well, let's see. Come on. All right, so here's case 8. So do we have a single angle? Yes? We have fasteners per line in the direction of loading. Let's look at case 8 here in a bit. Let's get to that here in a bit. Right now, let's just deal with case 2. Let's just deal with case 2. Now, I should ask for an angle, X bar. We need to look at X bar. I should ask whether or not we need to look up X bar or Y bar. But has anybody noticed something about X bar and Y bar for the L 8 by 8 by 5/8? They are the same. Why are they the same? Because this is an equal leg angle. If it is an unequal leg angle, they will not be the same. Okay? Because basically what we're saying is, how far do you get from here to the centroid? How far do you get from here to the centroid? Because these are the same legs, it's going to be the same distance. And by the way, what is that distance? 2.21. 2.21. Now, what is the connection length going to be for this angle? Along the length of the, or along the path of the load, outside bolt to outside bolt. Okay. From here, 2, 4, 6, 8, 10. So therefore, and so what is 1 minus 2.21 over 10? 0.779. Oh. Okay. Okay. So far, so good? Okay. Now, what about case 8? Okay. All right. So, case 8. What does case 8 say? Single and double angles. Now, it says we have 2 options. 4 or more fasteners per line in the direction of loading. 3 fasteners per line in the direction of loading. It says with fewer than 3, just use case 2. Okay, so it says fasteners per line in the direction of loading. So a line of bolts is however many bolts are in a line in the direction of loading. So how many bolts per line are in a line in the direction of loading? 3, right? So okay. So if we have 3 fasteners per line in the direction of loading, that's going to be our U value for case 8, right? So that means we have this. Oh, I had a boo-boo, and nobody caught it. It was 0.779, not 0.779 inches. U2 is unitless. The problem asked what is the shear lag factor. It didn't ask what the shear lag factors were, which means from these two, I got to pick one. Which one do I use? 0.6. Now, I'll say this. In 99% of the cases, that would be the correct gut feeling, because what you would do is you would want to use the minimum one, because the minimum one would correspond to a conservative estimate of capacity. But because these are empirical, what the manual says is the following. It says if U is calculated per case 2, the larger value is permitted to be used. And it says that because that fits the test data better, right? Essentially is what that's saying. So, between these, I'm going to use case 2. And this is probably one of the very few instances where I would lean in that direction. So, like, without that note, you'd be 100% right. 100% right. Okay? So, what I'm going to do is say, therefore, that's what I'm going to do. Does that sound good? Okay. Next homework. I don't know why that background's on like that. So, I'm giving you an L6 by 4 by 5/8. I'm using 7/8 inch diameter bolts. I want you to compute the shear lag factor, and I want you to tell me how long that member can be before it violates suggested slenderness limitations. And I'm giving you a hint for angles, because angles are unsymmetric. There are actually 3 listed R values. There's an RX and an RY, and then a principal RX about the Z-axis. And I think you'll see what I mean when you start looking at those. Okay. Sound good? I'm going to pull up the code one more time. That's all I got, everybody. See you on Wednesday.